Hi everyone, and welcome to my talk about how Rust compiles. In this talk, I'm going to talk about some of the details of the Rust compiler and what effects they have on your compile times and run times. Before we get started looking deeper into the Rust compiler, let's look at a quick example for which I've embedded the playground into my slides. Let's hope this works. I'm in the wrong place. Here, we have this code example here, which is in a library crate. We have a public function that has a local variable of type U8, an array of U8 with usize max as the size. That is a very large array, and it is in fact way too large. We will be able to see that there's a compiler error because the array is just nonsensically large. It would fill up the entire address space, and we can see the value of type array usize max is too big for the target architecture. So if we now add the inline attribute here, we wouldn't expect this to change anything, but in fact, this makes the code compile, which seems a bit weird. There's a good reason for this, though, and we will get into this later, but maybe during the talk, you can actually find out why this happens yourself. So let's move on. A quick bit about myself. As Stefan already said, I'm Nora, and I've been contributing to the compiler for about 4 years now, the last 3 of which I've been on the compiler team. In Rust, we love speed. For those who were at Conrad's talk yesterday about Z and speed there, speed is really important. We love runtime performance in Rust. We want our programs to be as fast as possible so our users can have very fast programs. But that's not the only speed we care about. We also like to have fast compile times, which in practice we are not as much satisfied there. But it's for a good reason, because we will see during this talk that actually compile times and run times are often in a sort of trade-off. And if we pick one, we lose some of the other. Why does this happen? Before we can get closer, let's take a quick whirlwind tour through the Rust compiler, at least some parts of it. rustc is way more complicated than could fit in the talk, of course, so we're just going to look at some of the parts that we are especially interested in. Compilers can be split into 2 phases, sort of. You have the front end and the back end. The job of the front end is to take the code, to analyze it, check it, do lots of things on it, and then afterwards the back end takes the result of that and generates the output, like machine code. In rustc, we have the source, of course, some random Rust function, which the front end then processes to what we call mir in the Rust compiler. Mir is an intermediate representation of Rust that looks nothing like Rust, and it's what the borrow checker runs on, and more notably, it's also sort of the bridge between the front end and the back end in the Rust compiler. Once we have this mir, we can feed it to the back end, to LLVM. LLVM is a code generation backend that's used by many different compilers, for example, rustc, but also Clang, Julia, Swift, and many more. And LLVM takes in this LLVM IR, which it then optimizes in many, many different ways, which is one of the large reasons why Rust is as fast as it is, because LLVM just does all of these crazy optimizations. After that, LLVM will emit machine code, like I've shown here, as assembly. So which part of this is slow to compile? We can look at the output of cargo build -- timings here, which separates each crate into a blue and a pink part, a purple part. The blue part is the front end, and purple is the back end. This is just building some random crate with debug mode, where we can see that the front end takes a bunch of time, but the back end also takes a bunch of time, which is the part we are more interested in today. Especially in release mode, the purple bars are going to be way wider, and it's going to take lots and lots of time in the back end. So why is the back end so slow? We could say it's LLVM's fault, but that's not quite fair. I mean, LLVM is not the fastest code generation backend that exists in the world as far as compile times go, but it's also not terrible. A big part of it is also just the reason that the way rustc generates the code, or rather, the way rustc invokes LLVM. To see a higher level, to better see what a compilation looks like, we can take a look at this here. This is cargo, which we usually use to build our programs, right? And cargo is not a compiler itself. Cargo calls out to rustc. We can see all the invocations here, which are very many and they are very long. And that's because every crate in your crate graph is one unit of compilation as far as rustc is concerned. So we have the crate, and the crate can be quite big. A crate can be on the orders of tens or even hundreds of thousands of lines of Rust code, which you can imagine takes a while to compile. C is quite different here, because in C, the unit of compilation, so the unit that one compiler is invoked on, is the single file, which usually is much smaller, except for like some weird files. And why does this matter? The reason that it matters, what C and Rust are different, is because of LLVM. LLVM is single-threaded. And because it's written in C++, this will not change. And this is mostly fine as far as C goes, because in C, you have many different files. They can all be compiled in parallel. So being single-threaded inside is fine. But in Rust, we have these large crates where not that many can be compiled in parallel, especially for incremental builds where we just change single crates. And there would be a problem to have a single-threaded backend. That's why Rust invented Codegen units. You have one crate, which then in the backend gets split up into many different Codegen units. And each Codegen unit is fed to LLVM individually and can therefore be compiled in parallel. There are about 1 to 256 Codegen units per crate, depending on the size of the crate, but also the configuration. Like with incremental builds, you have more for reasons. You can imagine it being like this. We have the main function here, and we have the mirror for the main function, which is the entry point for the backend as far as we're concerned. The front end did things to make this mirror happen. We don't care about that. There's like a trade solver or something over there, I don't know. And then the mirror is turned into LLVM IR, and this LLVM IR is put into a Codegen unit. This is then fed to LLVM, which produces an object file. Object files are files that are understood by the linker, that we'll get to later, which basically just contain the machine code for the Codegen unit. We then take the object file and all our libraries, like the standard library, and combine them into a single binary via the linker. This step is called linking. The linker is a big piece of software in and of itself, and it can also be a big reason why the builds are slow, at least for incremental builds, because linking has to be redone every time you build. There are faster linkers, which basically solve the problem of slow linking. On Windows and Linux, you can use LLD, which is actually the default now on Linux, x86-64 in the latest Rust versions. You can also use mold or even wild on Linux. Wild's being written in Rust, of course. That's why it's the fastest. And on macOS, Apple already did all the work, and the normal linker is fast, at least as of recently. So swapping the linker can help improve compile times on some platforms. Let's look into more Codegen units. In this case, I have two functions, and I have three functions, two of which are in a module. And the way rustc currently splits up Codegen units is that it creates one Codegen unit per module, and then merges the small ones until there are not that many anymore, depending on the amount that it wants. So we have our foo functions that get turned into one Codegen unit, and our main function is in another Codegen unit. We then compile both of these in parallel with LLVM, get back the object files, and link them all together. When we have multiple crates, we still have multiple Codegen units for each crate. In this case, of course, just one, because there's only one function. But if there are more, as before, they would be in the same crate. So we have our main crate and our math crate, as I called it. And in the math crate, we go to an object file, but then there's an extra step involved, which is creating what we call an rlib. An rlib is also a file understood by the linker from the binary format that contains all the object files for the crate. And you can imagine it's sort of like a tarball of all the object files here. And it's then also understood by the linker, it processes it, it includes all the stuff, and we get our final binary. And of course, the object files from the main crate and everything else. The standard library is also distributed as an rlib, in fact. All of your static dependencies are rlibs. So far, we've seen that we have these functions, I put them into Codegen units, and they get compiled, and that happens, and the more you have, the longer it takes, of course. We have generic functions, which is one of the reasons why just looking at the amount of source functions will not tell us how long it will take to compile necessarily. The way generic functions are implemented in Rust is via what we call monomorphization. Monomorphization means that for each different type that we call a generic function with, for example, U16 and U32 here, we create a separate copy of the function specific for that type. This means that if we have one function here, one add function here, and we call it with two different types, we actually get two different functions in the Codegen unit that have to be processed by LLVM separately. Monomorphization happens when going from mir, which is still generic, to LLVM-IR, which does not have generics. So we instantiate the function with the two types, have three functions in the Codegen unit in the end, which are compiled as usual. When we do this entire thing across different crates, it works a bit differently. The add function, which is generic here, is not compiled to machine code in the crate it's defined in, because there we don't know what types it could be invoked with. So we just export the mir for it and nothing more. And then in the downstream crate that calls this function with the two different types here, for example, we only then instantiate it, turn it into LLVM-IR, and compile it there. So we can see that in the main crate, we have three functions now, despite only defining one. That's the reason why generics are slow to compile, because for each instantiation, we have to optimize the function separately. But that's not everything. If two crates both instantiate a function with the same type, but in two different crates, both of them will get the local instantiation and have to optimize it on their own. This means that even if you are calling a generic function with the same type, it still may have to be compiled twice, or even more. There's a shared generics flag that's on by default that helps with a non-release builds where it's turned on, which means that if there's a parent crate that has a specific instantiation, like for example, vec push of U8, and a downstream crate calls this too, you can reuse the instantiation from there, but this doesn't work for two sibling crates since they can't see each other. So it doesn't help that much. Why did the sound no longer off? Okay. There's a tool, Cargo LLVM lines, which can help us see how many function instantiations we have in a crate, and can sort of tell you whether you're slowed down by lots and lots of duplicate instantiations of generics. But that's actually not the only way to get duplicate instantiation. It gets worse, because we also have inlining. Inlining is a great compiler optimization. It's even often called the most important one, for good reason. What inlining means is that we have a function call, like a call to our add function here, and we then replace this function call with the body of the function, like this, sort of. Not in Rust source code, of course, but in mir and LLVM-IR. And this is great, not only because it gets rid of the function call overhead of the function, but it also gives the compiler more context, which you can use to further optimize the code. Like in this case, thanks to inlining, we can now see that x is actually just 5, and we can constant fold it. But inlining has sort of a problem in the sense that if you don't have access to the body, you can't inline it. And that's exactly what happens when we want to inline across different crates. We have this add function here in an upstream crate. And this add function gets defined there, it gets codegen there, as I've shown before. And after that, we just have the machine code. But we can't inline machine code. We can only inline LLVM-IR and mir. So we can't inline this function. That would be terrible for performance. So luckily, at least there's a manual fix for that, which is the inline attribute. If we add the inline attribute to our add function, we will be able to inline it, because what the inline attribute does is it basically pretends that the function is a generic function. So in the math crate in this case, where the add function is defined, we just export the mir and don't do any codegen. And then in the downstream crate, we compile it to LLVM-IR in the Codegen unit where we need it. This means that if you have one function that's used in many different crates, every crate has to compile it itself, which is necessary to be able to inline the function in the respective crates. So if you have lots of these inline functions, it can really slow down your compile times. Inline is only really useful for non-generic functions, because for, at least mostly, Because for generic functions, they already get this instantiation mode by default, or rather they have to. For very small functions, like the add function, this actually happens automatically. We don't need to worry about it, so the example actually would have worked. But for every other function, it doesn't, because, as I said, if you have lots of duplicate functions, it's just very slow to compile. So if you're writing a library, you should consider applying the inline attributes to some functions where you've seen that your benchmarks can really profit from them being inlined across crates. But you shouldn't just throw it onto every function, because then the users will have very slow compile times and they will be sad. Another way to phrase what the inline attribute does is that it is sort of lazy with instantiation. And being lazy can have significant advantages if the function is actually just never called. This means that if the inline attribute is used on functions which are never called, they never have to be compiled at all, and you save compile times. That's the idea behind an experimental effort called hint mostly unused in Cargo, which you can read about on the blog here. My slides will be on the accessible at the end. You can just click the link there. And it's useful for crates like the AWS SDK, which is full of lots of different features, most of which people don't need. So if you apply the hints to these crates, they can be compiled significantly faster. But for crates which are commonly used, it will slow down compilation since everything will need to be duplicated. But say you're writing a binary and you just really want it to go fast. You don't care that much about compile times. Do you have to go around and just apply the inline attribute everywhere? That would be really bad. Luckily, you don't have to. You can use link time optimization. The idea of link time optimization is that you optimize all the code at the end together. This can break crate boundaries, because now it no longer matters whether a function is in one or another crate boundary. Everything is in the same place. We can inline whatever we want. It also slows down compilation even further, though. So it's not the default. To mitigate the compile times, there are different forms of link time optimization. The first one is LTO fat, which you can configure in the Cargo toml, though I think a better name for that is actually monolithic. We'll get to it why in the next slide. What fat LTO does is it compiles every function in the libraries to LLVM IR and nothing more. And then in the final binary, it will create an enormous Codegen unit with all the functions in it. This means that LLVM can now inline whatever it wants, since everything is in one Codegen unit. It also means that it will take forever. Like, I've benchmarked it a bit, and I've seen clean build compile time slowdowns of 2 up to 4 times. So in release builds. So only use this if you really want performance. But it can give significant performance speedups, all the way from like 0% to 10% or maybe even 20%, depending on what exactly you're doing, of course. Benchmark if you really want to know. And this is very slow. If only there was a better way to do this. Well, not necessarily a better way, but a different way to do it is LTO thin. I think a better name for that is actually sharded instead of thin, because thin and fat sort of imply that fat is just a better version of thin. But that's not true. Sharded and monolithic, or fat and thin LTO, other way around, are quite different. And they both have advantages and disadvantages. One advantage of thin LTO is that it's much, much faster. What thin LTO does is it also compiles all the crates to LLVM IR. It also generates a tiny summary for each function that shows basically how big the function is and nothing more. Then the thin LTO indexing phase, which is single-threaded but really fast, at the end comes and takes all of these functions, does some small light analysis on them and sort of groups them into different units, sort of like Codegen units, where they can then be compiled in parallel. But thanks to this index phase, what we can actually do is analyze which functions call which other functions and make it so that all the functions that call each other in the same place, sort of, and can be inlined, which is the main goal here. There are also some other intra-procedural optimizations that happen here. This means that we can compile things in parallel, which is great for compile times, but still be able to inline lots of functions all over the place. There's also a talk by the original developers of ThinLTO, which is very good and shows the entire thing in more detail. And ThinLTO mostly results in similar performance to FatLTO, I would say. It can be slower because there is still some parallelism here. We can lose some information sometimes, but it can also be faster, actually, especially for larger binaries, because because of the increased compile times, it's able to apply a few more optimizations, which could not be applied in FetLTO because it would just completely run away as far as compile times are concerned. So because of that, for example, the Rust compiler is compiled with thin-LTO because it's actually faster to do it with thin-LTO instead of FetLTO, as in the runtime is faster. The last sort of thing is linker plugin LTO, which can be done in both FetLTO style and thin-LTO style. The difference being that the merging of all the LLVM IR is not done by rustc, but by the linker. What this means is that it works across different languages, as long as they are compiled with the same LLVM. You can have Rust code compiled with rustc, and C code compiled with Clang, and everything comes together during LTO, and you can inline C code into Rust code and inline Rust code into C code. It's pretty cool. It's great if you have lots of FFI that has many different calls between the functions that in the languages that could be inlined, but it's slightly more annoying to set up, so if you don't, it's probably not worth it, but if you do, you should try it out. And actually, there is some amount of LTO that was here all along. LLVM can only inline things across inside the same Codegen unit without LTO, and we split the crate into many different Codegen units. This means that we would even lose some inlining between the different Codegen units. That would just be too bad for performance as a default. So what rustc does is it applies thin LTO between the different Codegen units in a crate, but not between different crates by default. We call this thin local LTO. So to summarize, how do you make your program run quickly? The most important thing is to let everything be inlined. Let the compiler inline your functions. It's not necessarily that everything needs to be inlined, but everything needs to be able to be considered for inlining as far as the optimizer goes. For libraries, this means add inline attributes to your functions that are commonly called and where the benchmarks show it's a good idea, so that even your users not using LTO can profit from the inlining. For binaries, if you want to go fast, use LTO. Try FetLTO, try thin-LTO, see which one is faster, and whether you can deal with the compile times. To get much more information about how to make your programs fast, there's also Nick's amazing perf book, which you can read online, that goes into much more detail about both ways to write Rust code to go faster, and also ways to optimize your build configuration further. I've shown you that you can configure LTO. There's so much more you can do to make your programs go fast. What if you want your programs to compile quickly on the other hand? As far as the source code is concerned, we want fewer functions and fewer instantiations. In LLVM IR, of course. In the source, it doesn't matter as much. This means that inline attributes and generics can really hurt compile times. But it's not just the source code you can modify. There are also lots of different changes you can make to your build configuration to improve compile times, which haven't fit into my talk here, but are linked by the blog post by Corrode, and also in the newly added page in the cargo book about build performance, which gives you lots and lots of different configurations, both stable and experimental, to try out. So if you have slow compile times, read these two resources and you may be more happy afterwards. What if you want both fast compile times and fast runtimes? As I've hinted to at the start, this is not quite as possible, at least at the same time. As you've seen, for example, the inline attribute, or just inlining in general, results in faster runtimes, but worse compile times. But of course, we can make use of the debug and release profiles in Cargo and configure them differently to both get fast compile times in dev mode and fast runtimes in release mode. There's also a bit something about the entire model being a bit suboptimal, which I won't get into more, but it could be that in the future we could improve the compiler in such ways as to make it that we can do more inlining with less duplication and sort of make the whole thing better. But it's been a long dream, but it's still far off, I'd say. So back to the start. Why did the inline attributes make this error go away? That makes no sense. It does, because this error is actually a special type of error. It's what we call a post-monomorphization error. This means that the error is only emitted when going from mir to LLVM IR, which is not true for most errors. Most errors are emitted much earlier. But in this case, since it's only emitted when going from mir to LLVM IR, what this means is that when we never go to LLVM IR, we never get the error, which is what we did when we added the inline attribute. Since it's a library crate, the function was never instantiated, and it's never emits the error. Now, if we wrote a binary crate that made use of this function, the binary crate would actually still emit the error because it's been converted to LLVM IR there. And with that, I wish you happy compiling. The slides are available on my website. And the next time you compile your Rust code, which, depending on which path you took, may either now be faster or slower, you will be able to think about what exactly the compiler is doing under the hood and sort of how it works. And you may notice that when you do this, the Rust code will compile faster than you thought. Thank you.